Awesome. So yeah, we'll just wait a few more minutes for people to join. Before we get started. But if this is your first blockchain event, welcome. Hopefully it'll be a good one. Hopefully you enjoy it. And what's great is this is the first one essentially of a 4-part series. So we've got another one tomorrow, part 2 of this technical introduction to blockchain. And then 2 more next week following on. So it's completely a continuous series. So do sign up to those. I'll put a link to our website where you can find the events in the chat. Other than that, still a few more coming in, which is great to see. Where are we? Awesome. Okay. Yeah, and also those are coming in, please say hi in the chat. It's something we did at the last event, and it kind of brings the virtualness to life a bit. So tell us, what you're up to. What do you study? Are you a student at the University of Oxford? Are you coming from somewhere else? Are you on the other side of the planet? Who knows? So just pop something interesting about yourself, what college you're at. It'd be great to see and get to know some more people. Laurence, just quickly with questions, would you prefer them to be done at the end?
No, I'm happy for people to ask questions as I'm going. It's sometimes a bit difficult for me to notice, but yeah, I guess if you put something in chat or I don't know what about, or if you can always interrupt if you want, Brandon, if there's someone with a question, and I'll answer it. I really don't mind.
Okay, cool. So yeah, so if you have any questions along the way, just pop them in the chat, and I'll try and choose a good moment to let Laurence know, hopefully not ruining his flow. But yeah, I think this is pretty much everyone, and we're at 34, 35 past. So let's get started. So yeah, okay. If you don't know me, or if you haven't seen my emails, I'm Brandon. I'm the president of the Oxford Blockchain Society for this year. Quite nice for getting everything back up on its feet, and especially virtually. So we're able to essentially get a lot more people into lectures and introduced to blockchain technology. A time like now, it seems quite interesting to learn about something like blockchain with, talks of PayPal introducing Bitcoin and Ethereum onto their payment system, allowing users to buy and sell those currencies. So the field is ever changing, and tonight we're lucky to have Laurence Kirk here from an Oxford-based blockchain consultancy, Xtrapy.io, where Laurence Kirk is the CEO and the senior blockchain developer. So if there's anyone, I'd say, based in Oxford who could give a great presentation on blockchain and is knowledgeable about it, it's definitely Laurence. So really take the opportunity to ask as many questions as you can, and sit in for the long haul, because this is part of a 4-part series where you'll essentially get to play a bit with Solidity by the 4th part. And I remember doing this 3 years ago or 2 years ago, and I absolutely loved it. So hope you enjoy, and over to you, Laurence.
Great. Thanks, Brandon. Thanks for that kind introduction. It's great to see so many people here. And shout out to the people. I'm also studying part-time for the MSc in software engineering, so shout out to the people here who are doing that. Okay, so I'll share my screen. Go. And okay. So yeah, a little bit about myself and my company. Yeah, we're an Oxford-based consultancy. We've been running for about just over 5 years now. We do development and consulting for companies interested in blockchain and cryptography, and we do security workshops. We do security audits, but we also do a lot of community education and a lot of workshops. Sadly, we can't do as many of those as we used to with lockdown, but so we're trying to do a lot more online. And also, yeah, I've been involved with the Oxford Blockchain Society since its start. So yeah, it's great to see it up and going again. Okay, so in the 4 sessions, this is the plan I have. So today we'll look at blockchain technology in general, look at some cryptography and how consensus works on blockchains. Then tomorrow we'll dig into smart contracts. We'll have some live coding of a smart contract on Ethereum. I'll go through the Solidity language and show you the development tools for that. Then next Tuesday, I think it is, the 3rd session, we'll look at decentralized applications. So that's taking your smart contract and getting a framework around that, writing a phone app for it or a web page for it and interacting with your smart contract. And then in the last session, we can look at associated technology. There are a number of technologies that very useful if you're working in blockchain. Specifically, things like decentralized file systems, storage, and then one of my favorites, zero-knowledge proofs, which help you with privacy and optimization. So we'll have a quick look at those. But all of these, if people want to discuss other things, that's fine. Just give me a bit of warning. We can change the direction if people want to do that. And as Brandon says, if you ask questions, you can ask questions as we're going along. Let me just get my chat screen up so I can see that. If I miss your question, yeah, please shout. I'm happy to stop and explain things, or we can hopefully have some time at the end. Okay, so today I'll talk a little bit about decentralization, then move on to an overview of what I think makes a blockchain. We'll talk about cryptography, do the background, everything you need to know about that. Then we'll look at consensus mechanisms, how they work in blockchains generally. We'll then have a quick introduction to programmable blockchains, which is really the start of what we'll be doing next week. So looking at what a smart contract is and what Ethereum is about. And then we've got time for some questions. But I think it's the concepts that you should be taking away, the big ideas, decentralization, trust. Blockchain is often described as a trust machine. Consensus, we'll look at in detail how we can come to consensus about a system, how we can verify systems and computational systems. Open systems, that's a very important aspect, I believe, of what sets systems like Bitcoin apart from other financial systems. Identity is very important, and resilience as well. Resilience of our systems against physical or malicious behavior, and how we can keep that even within an open system. Okay, we have problems with centralized systems. So a lot of blockchain, well, certainly Bitcoin came out of problems in 2008, the credit crisis then. But generally, a lot of people have problems using banks. There are a lot of unbanked people in the world. There's a lot of control the banks have over our money and our lives, and a lot of people don't like that, would prefer something less centralized. for example, the example I got there about WikiLeaks, and this was really my introduction to blockchain, I think, was when WikiLeaks was looking for funding, and all their funding got shut down through traditional sort of credit cards and all that kind of thing, and they had to go then to rely on Bitcoin for their funding, and which in the end they regarded as quite a benefit. But yeah, that's an example of money being controlled for political reasons. A great book, if you want to read more about this, is The Internet of Money by Andreas Antonopoulos. Well, any videos by Andreas are great, so yeah, I'd really recommend looking at his videos and his books. They are really very good. Okay, a great diagram of what centralized versus decentralized versus distributed systems are like. Really, I tend to think of decentralized being more like C actually than this, but this is a very famous diagram that was drawn before blockchain, but has been used very widely. The idea being that we have, rather than having a central authority and some nodes, some agents all connecting to that, we have some degree of decentralization where the nodes are independent, can make decisions by themselves perhaps, and can share information and are not dependent upon any central authority for being part of, say, a network. Examples of decentralized systems, they proliferate, and there are some examples in nature. A lot of insect colonies have some centralized and decentralized aspects. Wikipedia is to some extent, you might think that's decentralized. It might have a database, and interestingly, yeah, if you look at the number of employees it has very few. It's under 500, even though it's actually a massive repository of information. GitHub is, for those of you who know it, also comes out of the decentralized ideas and is often a good metaphor as well when you're thinking about how blockchains work. GitHub is very similar in the way that they work. And for those of you like me who were in development a long time ago, I remember using other systems like CSV and Subversion, which were centralized and quite clunky, and GitHub was a real breakthrough when that came around. Good question, is the internet decentralized? Well, opinion varies, but it seems to be getting more centralized as time goes on because of the tech companies like Google and Facebook. I'll link there to a mission to decentralize the internet if you're interested in that. I'll make these slides available. I'm not sure how best to do that, but yeah, I can make these slides available at the end. I'll skip that. There's a great blog here that compares decentralized and centralized systems. Some aspects that are worth pulling out, particularly for blockchain, we're thinking about decentralization, are things like flexibility, resilience, personal sovereignty. These ideas really resonate with me, the idea that people can have sovereignty over their money or maybe their data. I think it's a fantastic idea. On the negative side, they can be complex to manage. Well, of course, if there's no central authority, they are difficult to manage in that sense. And they can be difficult to scale. We probably won't talk about it today, but we can, in one of the sessions, we can talk about issues of scaling and how they are being overcome. Generally, I think that centralized systems are very fragile, and particularly, currently, there's so many people who are so interconnected. The connections between people and between systems and between devices has become so great. Centralized systems find this very hard to deal with. So decentralized systems, being much more flexible, can handle the complexity of the systems that we have in our society and our technological systems much more easily. It's interesting, I think, if you're thinking about how blockchains work, as a little mind game, just to think about something more like Monopoly. If you imagine you're playing a game and over the internet, but without some central copy of the software, where you can tell your moves to other people. And I know there's some, if you can do this if you're playing chess, you can email moves use snail mail moves to other people. But if you're doing something more complex, such as monopoly over the internet, it does present a number of problems, such as how can we verify the moves that someone else would make, or how can we verify the amount of money that somebody has within our game. And the ways we would solve this are probably that you would take your game and you would set it up locally and then try to replicate the system, the whole system, so that you kept track of what other people were doing, where they were on the board, the amount of money that they had. So you would have your local copy of the system, and that would hopefully be in agreement with everybody else's copy. But you would still have some problems, such as how do you know that the moves that somebody has made are valid, that if they've rolled a dice that really was what they did, and they haven't been just making up advantageous moves to benefit themselves. And we shall see how these ideas develop when we're talking about a digital currency, and how we come across the same problems, and how these have been solved primarily by the use of cryptography and consensus mechanisms. I don't know if there is, I think there is an interplay between centralized and decentralized systems. I don't know if there is an inevitable move towards decentralization, or whether that is even feasible, in the sense that it could progress in such a way that at any time there is an advantage to moving towards decentralization. I think that is an open question, and one well worth considering. Okay, there has been a lot of research on consensus mechanisms before blockchains came around. When people were looking at things like aircraft and systems in aircraft, how could they implement computer systems that were tolerant to either sensors being faulty or giving out misleading information? And so this phrase Byzantine fault tolerance was coined, which came from an idea of some generals attacking some objective, and how we would go about ensuring that they all received the same orders and all agreed on what they were going to do, even if there were some malicious actors involved. So the issues of consensus did not originate with blockchain, but as we shall see, it has been vital that those were solved, and when we're developing something like Bitcoin. And the other problem that was really solved with Bitcoin is the idea around double spending. If you have some kind of digital asset, you have the problem that if, say, Alice has some digital coin, how can we be sure that if she says that she has given this coin to Bob, that she hasn't actually also made a copy and given that to Charlie? How do we track that this coin is effectively unique in our system to some extent? And people, before Bitcoin, people tried to solve this really in quite centralized ways to keep track of coins. But with the Bitcoin, we had a breakthrough of the solution to this. Okay, so blockchain components. Now, I don't know if there is a proper definition of what a blockchain is. I tend to think of it as having the following components. For me, these are really the essential parts of something that makes up a blockchain. One of them is a gossip network. So if you've torrented music or software, you'll be used to the idea of peer-to-peer networks. Blockchains run on over the internet upon an overlay on the internet of a network, a peer-to-peer network, and these networks run via what's called the gossip protocol. The idea being that every participant in the network, every node on the network, will receive information and then gossip around to the other people that they know about on the network. And because there is no central authority in the network, there is no one to ensure that the information is passed around the network. And I won't go into how we ensure that nodes act fairly on this. That is a more advanced topic. But there is a protocol anyway to make sure that information is passed around. And joining and leaving the network is done on an ad hoc basis. There, again, no central authority. You don't have to ask permission to join the network. if you leave the network, that doesn't matter. The network as a whole can exist without you. Information can still flow. Other connections will be made between nodes, and as a whole, the network will continue to flourish. The most important part, perhaps, is the idea of a shared public ledger. And here I am talking about public blockchains. We'll perhaps see later the idea of private blockchains, but I'm going to focus today particularly on public blockchains. Ledgers are well known from the financial world. In banks, 100 or more years ago, they would have had a large ledger in which they would write down all of the transactions that happen in the bank. And the idea with a blockchain is that each participant in a system will have their own copy of the ledger. Now, I hate to use the word copy because this implies that there is a central version that is a single piece of truth. There isn't. So it's not a copy in that sense. Everybody has their own ledger that they maintain locally, and the updates to that are done via a consensus mechanism, by consensus in the system. And this ledger is shared amongst everybody on the system. And all of the transactions in the system are available to everyone, so everybody can fill in the transactions in their own ledger and be sure that those transactions are correct and update the state of the system according to the transactions they have received. The third component is cryptography, and we'll come on to that in a second. The reason for this is that we want to run our blockchain across, say, the internet, across a large network. We're interacting with participants that we don't know, but there is value in us having some idea of their validity or some degree of something about their identity, perhaps. Or we certainly want to know that the transactions they produce are valid. So for this, we need cryptography. Those components, give us some features for our blockchain system, or if we're using programmable blockchains like Ethereum, for the applications we write on the blockchain. And these are transparency and verifiable state. Because everybody has this public ledger, they all have access to all of the information that is on the blockchain, so they can verify that it is all correct, that all the rules that are in the blockchain are being followed. Resilience comes from the network, the peer-to-peer network, which can cope with people with nodes leaving or joining the system. Similarly, the network is resistant to censorship. If the government doesn't like what your blockchain is doing, they will have to effectively remove all of the nodes before they can shut it down. It's very difficult to censor a blockchain. And as you'll see with cryptography, the interactions that we have are seen as tamper-proof, so we can be sure of their validity. If we take a quick look at the history of cryptography and how this tied in with blockchains, really started, beginning of the 70s when the internet first was being developed, and there was a great breakthrough with public key cryptography, followed by Merkle trees, so hashing algorithms and Merkle trees, which I'll go into in a second. And then in the 80s, people tried to use this technology to see if they could come up with ideas of digital cash. So particularly people like David Chaum, who was doing DigiCash, was exploring these ideas. A lot of people did this, and then towards the end of the 90s, we had a development of peer-to-peer systems and networks for content distribution. But there were all problems in getting these things to come together and to solve some of the problems. And it wasn't really until 2008 that this really came together into an efficient, realistic implementation of a blockchain when the Bitcoin white paper came out. In fact, it was the 12th anniversary of the publication of that white paper a couple of days ago. Yeah, I mean, we should have a party next year, perhaps. I'll skip that. So if you go through looking about Indeed. If you go through a little bit about cryptography and how this developed, the problems we faced were ones of how do we ensure that messages, if we send them across a network, how do we ensure that they haven't been modified, and also how are we confident about the identity of the person that sent that message. And the first means of solving this, oh, sorry, there we go, a little graphic of Alice and Bob, the usual suspects, sending messages across the internet. Yeah, just to illustrate that. The first solution that was possible was something called symmetric cryptography. Now, this is the traditional cryptography that's been around for thousands of years, I guess. The idea that that people share a key. So, spies for many centuries had sort of code books, and they will encode a message and send it to another spy. And as long as they have the same code book, as long as they share the same key, they can encrypt and decrypt their messages. And even if their messages are intercepted, then unless that person has the key, they cannot work out what the message is. So this was fine, but the problem here with that is that you need some means of getting those keys distributed. So Alice, before we had the invention of public key cryptography, Alice and Bob would have had to meet or some way of giving each other a copy of this shared key. When public key cryptography was invented, we solved this problem, and we got the means of allowing people to communicate and to send encrypted messages without having met in person. And we do this by what's called public key cryptography, which is composed of a pair of keys, a private key and a public key. And these two keys are linked together mathematically. And you create this key pair, or you create a private key, and from that you derive a public key. And you can, as the name suggests, you can give your public key out to anybody in the world. And in fact, you want to do that. And people who have your public key cannot feasibly work out what your private key is. Your private key must be kept private, but you can be sure that even though you've given away your public key, nobody can work out what your private key is. Won't go into all of the means of doing that, but it's available there on the slides. So this was back in the 70s, this idea that came about. It was really a major breakthrough, and it's the basis of really all of the confidential and secure interactions that we have on the internet. The fact that you can use your bank, that you can make payments with credit cards over the internet, is all down to this invention that happened in the mid-70s. And the idea behind it is that Alice and Bob want to communicate. They create their own key pairs on their computers. So these are completely locally at this point. And they have a public key and a private key. And they can then share the public key on the internet so that other people can know their public key. And then if you imagine Bob wants to send Alice a message, so what he does is he has access to Alice's public key, and he can use that to encrypt his message. So he takes Alice's public key A, he encrypts his message below with that, and it comes out with something like the text that you see there. And he can then send that across the internet. The malicious user will not be able to make sense of that, but Alice, receiving that, can then decrypt that message because she has the private key that allows her to decrypt it. So she uses her private key to decrypt the message and gets back the message. So that's how we can send secret messages using public and private key cryptography. So a great advance, back in the mid-70s. But it doesn't solve all of our problems. Helps us with key management. It helps us with privacy. It means we can send messages without them, without worry. Even though they're intercepted, we don't worry that they are being intercepted. But it doesn't solve the question of authenticity. Of how can we ensure that the message came from the person that we think it came from. And this was solved with the invention of digital signatures. And effectively, it's very similar to how we send secret messages, but really done the other way around. So in this case, rather than signing a message with somebody's public key, what we do is we sign a message with our private key. And so if Bob wants to send Alice a message, what he will do is he will create the message, he will sign it with his private key. Now this means that anybody with his public key can decrypt that message. So this is not about sending secret messages. It doesn't keep your message secret. But what it does do is that if you use Bob's public key to decrypt the message, and you're able to decrypt the message, then you know that it came from the owner of the private key that goes along with that public key. Now, digital signatures are there's a little more to them, and the whole area is a little more complex than that. But that's the thing to bear in mind in terms of the blockchain. This is the most important use of public and private keys that we have in the blockchain, is the idea that we can be sure of who sent a transaction on the blockchain, because the person who sent that transaction has signed it with their private key. So the transaction itself is not kept secret. We want people to know what our transactions are on the blockchain, but we can be sure that once we see a transaction, that we can associate a particular public key with that transaction, because we know that a certain private key was used to sign that transaction. And blockchain systems vary, but the blockchain address, the wallet address that you have on a blockchain, such as Bitcoin, you have a Bitcoin address or your Ethereum address, that is not exactly your public key, but to all intents and purposes, it's your public key. It's derived from that. I mean, on Ethereum, it's kind of a shorter version of your public key. So in terms of cryptography and public-private key cryptography, this is the use that we have with the blockchain. And digital keys have these various properties. Really, we're interested in authenticity and the fact that these transactions are then unforgeable, unalterable. Yeah. Okay, so that was that part of cryptography happening in the 70s. 70s is a great time for cryptography. At the end of the 70s, Ralph Merkle, who is a real giant in the blockchain space, really, in what he did for this area, introduced Merkle trees and versions of hash functions. And hash functions are really the second important area of cryptography that we need to understand that we really use in a blockchain. The way I like to think of hash function is that they're a way of taking a fingerprint of some data. So the hash function itself is not secret in any way. These are well-known, published functions, standard functions that are standard bodies will publish. So everybody can know what these functions are, or know how they work. But the idea is that if you pass some data through one of these functions, so here we're passing a piece of text, Loughborough, and putting it through a hashing function, the output that we get is some bytes, some hexadecimal bytes. And there's a link there if you want to try out a particular hashing function. One of the most common ones, SHA-256, is available. You can try this out. So you take your initial data, and you put it through this function, the hash function, and it gives you an output. And that is what I like to think of as a fingerprint of your data. And each time, if you put the same input into the hash function, you will always get the same output. So it uniquely identifies the data. Well, it uniquely identifies it because, one, it's repeatable. If you put the same data in, you always get the same result. Also, there's no hash collisions, so that the data that you get out will only be produced by that particular input. And then the other important point about the hash function is that it is a one-way function. So it is computationally very simple to go from left to right here, to take some input, to put it through the hash function and get an output. But it is unfeasible to do it the other way around. Given an output, it's computationally not feasible, prohibitively expensive to work out what the input to the hash function would be to give you that output. So, we have an example here, the uniqueness of the hashing functions. So if we change the case of a letter in our input, we get a completely different output. So it's given some output, you cannot guess, easily guess what the input would produce that output. Okay, and we use this in a couple of ways in blockchains. So the first way is to do a fingerprint. So we can take a fingerprint of the data, and this helps us understand whether that data has been tampered with when it's been passed around the internet. The second way is used, as we shall see, is in the Bitcoin consensus mechanism as well. It's there we rely on this idea that we cannot easily go back from the output, easily to go back to guess what input would produce a particular output. Okay. And we use these, where Merkle Merkle trees come in, is that we can put these, we can combine hashes. And so blockchains do this a great deal in that they can summarize data and summarize sets of transactions. So they can build up trees of data. So if you have here, for example, we have 4 pieces of data, we can take those and produce output. We can hash them each individually and produce 4 hashes. The outputs of these functions are of a fixed size, so they'll be 32 bytes. But we produce those of each of these. But then we can then put those hashes together pairwise and then produce a hash of the result, and so on until we get to what's called the root hash. And this, the whole thing is called a Merkle tree, and it's obviously it can be much bigger. But it is a binary tree. It could be many more levels than this. In reality, this is the kind of results that you would see. This is what it would look like if you did this. And it's useful because you can then, if you're given part of the information through this tree, you can then check whether the information is correct. So you can validate part of the tree by going up just one kind of branch of this tree and then going up and recalculating everything up to the root hash. So you could say that if you know what the root hash is, you can check if somebody tells you that the original data is E, you could take a hash of that. If you know what the data C is, you could take a hash of that. And then you could check whether that the data, the hash there, should equal the hash of C and D, so the green box there. So here we see that the D has been substituted for E, and so the hash of C and E is not the same as the hash of C and D, and then if you took it further to the root, you would get a different root value. So it's a way of checking quite easily, quite simply, whether data has been changed within a large data structure. So that's the some of the basics of cryptography. I've gone through it quite quickly. I hope it makes sense. You don't have to understand it in a great deal of detail, but just pick out some salient points, such as the difference between public and private keys and how they are used in the blockchain, and the fact that hashes are used as a digital fingerprint in the blockchain. Probably a good place to pause for any questions you have about cryptography. Or if you want, I can, yeah, you can leave them to the end. Okay, I'll go on to how it's used in blockchains later on. So I think it'll become a lot clearer. Then it was a lot more concrete. But this technology was developing back in the 70s and the early 80s, and people started to look for ways to use it to develop things like electronic cash, maybe time stamping of data so that you could prove, maybe you want to prove that you've invented something, a patent, you have a patent for something, you want to prove when you had that, things like this. So all of these ideas were being developed in sort of the end of the last century. A couple of attempts were made at electronic cash, given there's some links there if you want to look at them. But neither of them really solved all of the problems to make a really working solution. And it was only in 2008 that when the Bitcoin white paper was published, that we got a real working implementation of a blockchain. And this was published by Satoshi Nakamoto, a pseudonymous person. Nobody knows who he, she, they are. Certainly not the person pictured there. That's he had to put out a disclaimer by his lawyers anyway to say he's not Satoshi. If anybody knows who Satoshi is, it's yeah, it'll be solving a great mystery. But yeah, whether it's one person, many people, a time traveler, an alien, yeah, we don't know. But fantastic invention, dependent on many good ideas on cryptography, but also bringing in ideas around game theory, and really it solved problems around open systems as well. So the ideas in financial systems, if you think about the way they solve security, they have lots of security in place. Banks have lots of security to prevent malicious people interfering with their data. And what we were trying to do, what Satoshi managed to do with Bitcoin, was to solve these problems in an open system and to say that here is a system which anybody can use. We're not going to permission this in any way. So malicious people can use it. They can try to do malicious things if they want to. But the system itself is so robust and is created in such a way and is incentivized in such a way, and it's incentivized by a field called cryptoeconomics. But all of that is built into the protocol of the system. It is done so well that the system is robust to any of the attacks that could happen. The question, would Merkle tree for proof of work? So the Merkle tree is used particularly in, we build up Merkle trees in transactions. So it's a way of getting a large number of transactions, of getting a fingerprint of those transactions into a block. The proof of work part is just what is more of a simple hashing function, where, but I will come on to that in a second. Okay, so Bitcoin, great system. It's 12 years old. It's been going without problems, really. I mean, it's survived since then in a very hostile environment. Fantastic that something could survive that long and still be used and still be available globally. Absolutely fantastic system, I think. The slight history of it's there. yeah, it was October when the paper was published on a mailing list. And then the beginning of 2009, when an actual software implementation was released. Not used a great deal initially. Very famous example in 2010, where somebody bought pizzas for 10,000 bitcoins. I always forget how many that is, how much that's worth now. But I think the current Bitcoin price is around $13,000. So yeah, you can do the maths. But yeah, if you'd held on to those bitcoins, you'd be very rich indeed. At the moment, it came out of the financial crisis, and the first Bitcoin block, called the Genesis block, block 0 in the Bitcoin blockchain, had a data area, so you could put data into it, and Satoshi put in the headline from the Times of that time, so talking about the second bailout of banks, giving a kind of a timestamp, I guess, of when it was produced, and also showing a little of its the reasons why we really do need Bitcoin. I won't go into B money and what that looks like. If we think about, is Bitcoin decentralized? I think so. It is arguable. There are problems about its centralization, but there is no central authority, no central server, which is made up of participants running nodes and having wallets on the system. Anybody can download the whole ledger. They can look at every single transaction that has ever happened on Bitcoin. We'll talk about the incentivization in a second. The issuance of Bitcoins is decentralized. It is done as part of the protocol. So there's no, a bank could, for example, decide to issue more banknotes and increase the money supply. In Bitcoin, we know the rate at which the supply is growing. And there is, in fact, a fixed amount of Bitcoins so that will be produced. So we will only ever have 21 million Bitcoin eventually. And it is a public blockchain, so it is completely permissionless. There's a little timeline of how it came about. And it did solve the real difficult problems of the time. The consensus mechanism was used to solve the idea of how we can agree on updates. So our Byzantine generals problem, and it effectively solved the double spending problem. That was really the big breakthrough, the fact that we could have a digital asset that couldn't be double spent. Another way of looking at the type elements of the blockchain as well. So I've spoken about peer-to-peer network, digital signatures, hashing functions. We timestamp the transactions and the blocks in our system. And we have this thing called proof of work, which is our consensus mechanism. So our means of coming to agreement about what is happening in the blockchain. Okay. Just a quick review of how the public-private key cryptography works. So with our public key, we effectively get an account address. So if you want to have a wallet in a blockchain, you will effectively derive that from a public key. Sorry that this slide has not worked properly. Those dots should be below. So the public key gives your account address, allows you to receive money. That is the address you'll give to other people if you want to receive some Bitcoin, for example. And then your private key is used to sign transactions, and it is only with your private key that you can spend money. So your private key gives you complete control over your Bitcoin or your digital assets. And certainly the saying, if you don't own your keys, you don't own your coins, is very true. In reality, people allow exchanges, centralized exchanges, to create accounts on their behalf, and the exchange will hold a private key. But if you want to truly feel in control of your digital assets, then you should create your own private key and hold that. And then that gives you absolute control over that asset. And unless you somehow leak your private key, then nobody else will be able to spend that asset or control it in any way. Okay. This diagram is a kind of generalized, idealized idea of what a blockchain data structure would look like. All blockchains are different and they will do their data structures in different ways. So in reality, it may not look exactly like this, but this gives you an idea of the important parts. So our blockchain is made up of a number of blocks. These are produced usually at a fixed interval. In Bitcoin, we have a new block every 10 minutes, roughly. In Ethereum, it's maybe every 12 to 15 seconds. But the blocks are produced regularly. Each block has two areas. There is an area of transactions. So this represents the latest transactions that have happened in the system since the previous block. And then the other area is called the header. And this has a number of items in there, has a timestamp so that we can know when this block was produced. But it also has a link to the previous block header. And this is how we achieve security and in our system, and how we chain our blocks together. So that's where the terminology of chain comes from in our blockchain. So the idea is that we start off with block 0, our Genesis block. You saw the example of the Bitcoin Genesis block. And this has a header, and it could have transactions, or it may be empty. And then the next block along will have some transactions. It will have its own header, and it will have a fingerprint, a hash of the header from the previous block contained within its own header. And then the next block along will do the same thing again. It will have some transactions. There will be a hash of those transactions in the header as well. So there'll be a fingerprint of the transactions in the header, and there will also be this pointer back to the previous header, the previous block header within the current block. And so this means that if somebody presents you with a block and says this is block number 2, then there's a way that you can verify that the blocks are in fact valid because you can go back and you can check all of these block headers and check that the hashes of all of these match up. So you can take an original block, say block 0, and look at the header of that. You can take the fingerprint of that, so take the hash of that, and then see if that matches the hash that is in block 1. If that is correct, then you can take the hash of that header and see if that matches what is in the header of block 2, and so on, right up to the current block. Which means that if somebody tried to come along and make a change in one of these blocks, say somebody came in and wanted to change block 1, if say they changed the transactions in block 1, they would have to then change the header in block 1 because the header contains the fingerprint of the transactions. But if they change the header in block 1, then they would have to change the header in block 2 because that has a fingerprint of the block 1 header. And if they change the header of block 2, they have to change the header of block 3, and so on up to the most recent block. And so that means that the work you need to do to make it, if you want to falsify information, is a great deal of work. You have to effectively produce new blocks since the block you've altered right up to the present time. So let's look at the question. If anyone can become miner. Okay, so I'll come on to how the mining works in a second, and we'll see. So hopefully I'll answer your question in that. Hopefully it'll be clear. Okay. So you can, when you create your public-private key. You do this in your own wallet. You do this locally. You don't need to ask anybody's permissions to create your private key, to create your account. Is entirely up to you to do that. And this always confused me when I first came across blockchain. I wondered how could you create your own account? Wouldn't that, how do you know this wouldn't conflict with somebody else's account? And effectively, you don't know that. Really, you're just doing this by the fact that when you create one of these private keys, you're assuming it's going to be different from anybody else's, just because these keys are so large. So you create these at random, and so the chance of two people at random creating the same private key is sufficiently small that you don't have to worry about it. So the question, would it be easy to change a recent transaction? Yes, so you could, if you looked at the, say, a previous block, so block N, you could try and change a transaction in that, and then you would only have to change the most recent block. And we'll come on to how that would work. If two people have conflicting views of the transactions in a block, how we resolve that. Yeah. Okay. Oops. Okay. What time have we got? Maybe I want to. Okay, plenty of time. Okay, so talking about transactions now and how that works in Bitcoin. So imagine Alice wants to send 1 Bitcoin to Bob. So we get our public and private keys. We've got our public key, which gives us an address. So this is Alice's effectively address, and she has her private key. And also we have Bob similarly has his private key and his public key and his address. And so we want to make a transaction. So what Alice has to do, and she can do this offline, is that she creates the instructions, really saying what she wants to do. That she wants to send a certain amount of this cryptocurrency to Bob. So in this example, we're going to send 1 Bitcoin. So we start assembling a transaction. So we say we want 1 Bitcoin. We send in the transaction our public key. Alice sends her public key along. So we're saying who this transaction came from. But this will be verified. This can be verified by everybody who sees this transaction. But it is a way of saying what address, what wallet this money came from. And then we have to obviously add in Bob's address, because this is where the Bitcoin is going to go to. And then we have to sign it. So we have that information, but then we have to sign it so that we can prove that this did indeed come from Alice. So she does the signature by using her private key. And so that assembles the transaction, but it doesn't go directly to Bob, because Alice doesn't know anything about Bob necessarily. She knows his address, but that's probably all she will know about him. She doesn't know whether Bob is online or has access to the blockchain network at this particular time. She really can't make that assumption. So she's not sending this transaction directly to Bob. Now, there are some systems where you can send transactions direct to people. I'm not going to go into those. I'm talking really here about just normal transactions. So this is really how normal transactions work on the blockchain. So she doesn't send it directly to Bob. What she does is she broadcasts that transaction to the Bitcoin network. So this transaction she will give it to a node. So she will connect in some way to the blockchain network, whether that is the fact that she's running her own node on the system, or maybe she just passes the transaction off to a node that she knows about. But she has to in some way give this transaction to the network. And then the peers on this network, they are operating this gossip protocol. They will gossip this transaction around the network. So everybody on the network will get a copy of this transaction. And they do some validation on that transaction before they send it on. because they can verify that it came from the public key that it claimed to come from. So they can check the signature of the transaction at this point and say, yes, this actually did come from the public, from Alice's address, effectively. So we can check that using that public key, we can check that against the signature and know that the private key associated with that public key was used to sign this transaction. So we know it did in fact come from this particular address. So, and as a shorthand, we can say, yes, we think then, this person is Alice. But we can verify it before we pass it on. So all of the peers in the network will verify that. They can also verify that Alice is allowed to spend this because they all have their own copy of the ledger. So they all will know how many Bitcoins Alice will have. So they can check whether Alice indeed has a Bitcoin to spend and give to Bob. And so if they find out that Alice doesn't actually have one Bitcoin, so she can't actually send a Bitcoin to Bob, they can stop the transaction at that point and say this is an invalid transaction and just drop it and not propagate it. But otherwise, they will send it around the system so that everybody gets it. I'll come on to how this is put into a block in a minute. Just to mention, there's some terminology you'll come across called UTXO model, and this is a difference in the way that Bitcoin and Ethereum work. I don't want to go into it in detail, it's a little complex, but effectively on Bitcoin, you don't really keep track of the accounts as such. You don't have a way of saying, or you don't keep the information together of a particular account and the balance it has. Instead, what you do is you have a way of looking back through the transactions that you have in your ledger to work out that value. So it's done by knowing that Alice has had sufficient Bitcoins been sent to her, that she has enough that she can then send one Bitcoin onto Bob. And this is different to the way that Ethereum works, where they do keep track of the accounts and the balance of that account. So the Ethereum way of doing it is to some extent simpler. It's easier to understand and it's easier to program and to deal with. But it does have some disadvantages in other ways. So it has some overheads doing it. But in Bitcoin, you have this thing called the UTXO model, and different blockchains may follow that model. Different cryptocurrencies may use a UTXO model or an account-based model. They do vary. Okay, so that's how we get a transaction out into our network. But then how do we come to some consensus about that? And how does something that people have already mentioned, how does mining work? And how do we prevent people doing malicious things in our network? Hopefully this will answer all your questions, but please do keep answering questions, asking questions. Okay, so I'm going to look at this from kind of a network point of view. So these dots represent nodes on our, say, our Bitcoin network, and each node is connected to some other nodes in our network. Obviously, the real network is much more complex than this, and there will be many more connections, many more nodes. And we assume here Alice has a connection to some node, whether she's running it herself or in some way she has a connection to it. And at the bottom here, we have this blue block, which represents the latest block in our blockchain system. So, we could be, this could be block, 1 million or so in our blockchain system, whatever it is, but it's the latest one that we have. And it's important to realize that this block, effectively, this block and the information in the previous blocks, but the state of the system is all represented within that block. And that is the one truth about the system is represented by what is in the blocks. As we've said, I kept saying and emphasizing, there is no central authority. So if you do not agree or you do not like what is in that block, well, I'm afraid that's hard luck, because you cannot appeal this in any way. The whole truth about our system is represented by the latest block and the previous blocks. That is the only source of truth in our system. And what we're looking at now is how do we come to agreement about what that truth is in our system? How do we come to agreement about what the current state of our system is at any one particular time? So we imagine here that Alice wants to make a transaction. So she wants to say, send some Bitcoins to Bob. So she will send a transaction off to a node. And as we saw, this node will then propagate this around our network. And at some point, this will be put into a block. A new block will be produced containing Alice's transaction. And that will become the latest block in our system. And I have a little arrow pointing backwards here just to show the chaining. So the fact that this block has a link back to the previous block header. So that yellow block then represents the latest system, and it includes Alice's transaction. So the state of our system now includes whatever Alice has done in our transaction. And we're assuming here that Alice has made a valid transaction. And then at a later time in Bitcoin, after another 10 minutes, another block will be produced by a different node on the system, and so on. But the question arises, how do we come to consensus? That's really the question we're trying to solve here. And really the big problem that was managed to be solved by Satoshi when she invented proof of work. And that is, if you imagine in our network, this is a global, a geographically distributed network. There could be transactions in one part of the globe, that's represented here on the upper left, so by the grey transactions. Other transactions here on the lower right, the green transactions. So at one point in time, we could have this situation where any one node on the system might have a different view of the state of the system, because they may have seen the grey transaction, or they may have seen the green transaction, or they may have seen neither transaction. And we don't want this. We want there to be consensus about our system. We want people to be in agreement about the state of our system. So how do we achieve that? And what we do, in this proof of work consensus mechanism, is to say, well, all of these nodes on the system are effectively equal. No one is special in any way. We don't have any central authority. No node is special here. So why not just pick one of these nodes at random and ask them what their view is of the system at a particular point in time. And our protocol will say that we will agree to whatever they say their view of the system is. So we will pick this node at random. They will tell us what the state of the system is, and they do this by producing a block. And everybody will then accept that as being the state of the system at the time that that block was produced, which is a great solution. Solves our problem nicely. It's a means of getting a consensus. But there is a drawback. You may have known. You may have what they said. There's a problem with this, and that is we don't have a central authority. So how do we pick one person to produce the block? And the way that we do this involves this process called mining. And the way it's done is that we allow nodes to run mining software. Now, you don't have to do this. You can be part of the Bitcoin network without running mining software. But if you want to produce a block, you need to run mining software to produce the block. And what we effectively do is we say, the way we choose this person to produce the block is that we will all enter into a race. So we'll all go into a race, and the first person to win this race can then produce a block. We will be able to verify that that person won the race, and I will explain how in a second. But the person that wins the race produces a block, and when people receive that block, they can verify that that was indeed the winning, from the winning person, the winning miner, and they will accept the block as being the valid state of the system at that time. And this race is a race to solve a mathematical puzzle. And this puzzle is extremely difficult to solve. And this puzzle is very simple to describe. It is very simple to try to solve, but it is very difficult to actually solve. So the puzzle involves the following, and I'll say this a few times if I explain it badly, so please make sure you follow. What we do is each miner takes the data that they have that they want to put into the block. And that is kind of the basis of the puzzle that they're going to solve. So they take that data and they add to this a guess, a random number. And to solve this puzzle, what they have to do is to guess this number correctly. So they take some data that's going to form the block. They add this random number to it, and then they take a hash of the whole thing. Now, that is very easy to do, and they can do that very quickly. And then, having done that, they will get some output. So they take their data, they add a number to it, which is they do at random. So say their number they do at random is 100. They add that to their data, do a hash, and it comes up with a resulting output, a resulting number. And what they then do to see if this is the winning number, if they won the puzzle by doing this, is they check whether this number is small enough. So you have to see whether the output of your hash function is below a certain amount. This is in Bitcoin, the amount, the size that it has to be is extremely small indeed. This is why it's so difficult to do. So you will make a guess and you will put your data through this hashing function along with your guess, and the result you come out with will be too big. Most of the time, you'll make trillions of guesses, and there are tens of thousands of people doing this all around the world, making billions of guesses each second, well, trillions of guesses each second, and it takes, on average, 10 minutes for one person in the world to find that number that, when added to their data and put through this hashing function, as an output, gives a value that is small enough. But when somebody does that, they will produce a block. And in the block, they will put their data so people can check the data. That was their starting point. They will put this random number that they guessed. This is their winning number, which is confusingly called a nonce. They will put that, and then they will pass that block around. And everybody who receives that can then check that that data plus their guess is in fact, does result, when they put it through a hashing function, with a small enough value. And the beauty of this is that to guess this number, this nonce that you're trying to guess, this random guess, is very difficult to get it right. But to verify it is very simple. You can do that in a fraction of a second. So if you already know the answer, you can verify that it does indeed solve the puzzle very quickly. So the nodes in the system that receive this block can instantly verify that the puzzle was solved by that person. But to actually solve it and come up with this winning number is very difficult and takes a long time. So just to talk about a replay attack. Because that's come up in the chat. So a replay attack is the idea with transactions where just to go back to transactions and showing they're valid, you could say, what happens if Alice has sent her transaction to Bob to spend 1 Bitcoin? What happens if somebody makes a copy of that transaction and then sends it again? Would then Alice end up sending 2 Bitcoins to Bob? I mean, maybe Bob would do this. Maybe he would do this a few times and say, well, here's 5 transactions sending me 1 Bitcoin each. I'll get 5 Bitcoins. And the way this is solved is by this nonce solution. So Here, unfortunately, nonce has a different meaning, but effectively what happens is that we keep track, when transactions go out from an address, we keep track of a number, an increasing number. So if we replay, if we resend the transaction, we can see that that transaction has been sent before and we can ignore it. So it's impossible to have duplicate transactions in our system. So you can't do the same transaction twice. So Bob can't send himself lots of transactions from Alice. He can only ever benefit from one transaction from Alice. So that's the idea of the nonce attacks. Okay, so that's the idea behind mining and how we come to solve, to produce a block, how a miner produces a block, and how we solve this puzzle and how we get the state of our system at any one particular time. And I should explain a little bit more about the mining, that the miner, when they produce the block, what they do is because they're a node on the network, they will have received a number of transactions. So they take those transactions and assemble them into the block. And they can choose which transactions to put in that block from the ones they have available. And there are various incentives that the miner has to do this and to do this computation, because doing this computation is very expensive, but they are incentivized in two ways. One is that when they produce the block, they can add in a special transaction. And the ability to do this has been agreed by everybody who uses Bitcoin. So it's part of the Bitcoin protocol. But the person who produces the block adds in a special transaction which pays themselves a certain amount of Bitcoin. Now, and this is how new Bitcoins are added to the system. And effectively, this creates Bitcoins out of thin air, because there is no wallet that is sending that Bitcoin to the miner. It's just the miner themselves saying, my wallet now has more Bitcoins. But the amount they give themselves is decided in the protocol, although it does change over time. So at the moment, it's just over 6 Bitcoins. But every few years, it goes down by half. So it was, until earlier this year, it was 12.5 Bitcoins, and it's just gone down to just over 6. I think that's right. So that's the main reward, and this is called the block reward. So the miner themselves includes a transaction in their block to say, I now have 6 more Bitcoins than I did before, and that's my reward for doing this, for mining this block. And then the other incentive they have is that every transaction within that they include in their block will include a transaction fee. So this is a small payment that goes to the miner, and it goes to the miner from the person who sent the transaction. This is much smaller. So typically this should be at the size of maybe a few cents on Bitcoin, but it can vary, and this can produce problems. But it should be that kind of size. So each transaction there'll be a few cents worth of transaction fee, sometimes called a network fee, that will go from the person who started the transaction or go to the miner. And so the miner will get those fees as well. That's, at the moment, the amount they get from fees is not as much as they get from the block reward. But as this halving happens, so as this amount of the block reward goes down, eventually it will get to 0. And this won't happen until the next century, but it will eventually happen. So at that point, there will be no new Bitcoins being made. And this is how we know that there will only ever be 21 million Bitcoins in circulation at most. But at that point, the miners will still get fees paid to them from the wallets of the person doing the transactions. So how that will play out is people are not sure about. It may be problematic, but I don't know. I'm not going to be around to see it, sadly. So a couple of questions. The ideal size of the blocks, that's a contentious question. This has changed as there are different views about this. So initially, there was the idea that I think it was 1 megabyte blocks was the physical size for Bitcoin. Then different schools of thought arose in the Bitcoin community. Some people wanted larger blocks. Some people wanted to keep the blocks the same size. And so there are now differing protocols. So the software has forked. We have different networks. So we have so Bitcoin Cash, for example, has different size blocks to Bitcoin. And there are also other ones with different size blocks again. The ideal size, if you have larger blocks, you can get more transactions, but then they take longer to pass around the network. So there are pros and cons to increasing the size of blocks. The number of Bitcoins currently in circulation, I don't know. It's not far off 21 million. I think we've got, I think it's certainly over 50% of that. But I don't know how many there are currently in circulation. I should point out that Bitcoins are divisible into much smaller amounts. Obviously, you don't want one Bitcoin to be the smallest amount that you can send. So you can send fractions of a Bitcoin around. The smallest denomination of a Bitcoin is called a Satoshi, which is a very small amount indeed. But yeah, I don't know. Okay, thank you. Yeah, there you go. So we've got, most of them, about 18 million. So I've got most of them have already been produced, but it won't be until next century they'll get up to 21. Okay. So that's mining. Yeah. So the reason this is secure is the fact involves doing this puzzle, because to do this calculation, to solve this puzzle, requires a lot of computation. So for one miner, if you have to do this computation, make trillions of guesses each second for 10 minutes, in terms of computing power to do that, that is a significant amount of computing power, which means a significant amount of energy that is needed to do that. So to produce a block and have it accepted by the network has a real economic cost. And this is where the security comes in, and where the question about the most recent block makes sense, because yes, if you want to produce a block along, the most recent block, then you can just produce one block, and that will cost you a lot to produce, a lot of energy, but it will be less than the cost. It will be less than 6 Bitcoins. Otherwise, it wouldn't be viable to do this. So it may be tens of thousands of dollars, but it will be of that order. But if you wanted to go back and change the history and go back 50 blocks and change the kind of the blockchain from that point up to the current blockchain, up to the current block, to produce 50 blocks would be a massive amount of computation that you would have to do. And so this is how our system is secured. It is the amount of work that is needed to be done to produce the blocks that stops people producing malicious alternative histories, if you like, of the blockchain. Thank you, Judith. There's an economic incentive to following the protocol and to produce an alternative history of the blockchain. And so the crypto economics of this protocol that secure the blockchain. And that is, I think, a fantastic thing. The fact that Satoshi came up with this idea and aligned these incentives in such a way that this protocol could be put out to the public and left to run for 8 years, and it still works, is an amazing achievement, I think. Yes, to answer to Ray, yes, if you produce the nonce, if you know the answer, then yes, you claim the reward. But obviously, you're not going to tell that to anybody else, because they could also try and claim the reward. So if you get the magic nonce, If you know how to produce that magic number that lets you solve that puzzle, you'll put that in a block and get it out along with your transaction that pays you the reward as fast as you can. And you don't want anybody else to get that. And that brings me nicely onto what happens if two people produce a block at the same time. So next slide, just to go through the blocks we produced again. What happens if we get this kind of situation? So we were going along happily. We produced a blue block, we produced a yellow block, and then the miners were mining away, trying to solve the problem. And at the same time, roughly, the red miner produced a block, the red block, the green miner produced a block, the green block, and they thought they were the latest to produce it. They didn't know about the other block coming out. So at the same time, they say, here's the latest block, this is the latest one, and it follows on from the yellow block. Now, we don't want this, because here we have a break of consensus. We want to be in agreement about our system, but potentially here we have disagreement about the system. We have two alternative versions of reality here. We don't want that at all. So we have to have some means of deciding which of these blocks we're going to accept as being the latest block. And to do that, we have a very simple heuristic. We just say we're going to choose what's called the longest chain. Now, here, I know it looks like they're both of equal length in terms of number of blocks, and that's true, they are in terms of number of blocks. But there is a way of looking at how much work has been done in solving the puzzle in each of these blocks. And so there will always be a way of distinguishing between two blocks that you get. So there will always be a way that someone, if they see the red and the green block at the same time, they will also be able to decide which one is really the latest block, and the one that they should take as the latest block and the one they should follow on from. And so if we imagine here, we have the next block being produced, this beige block, and they have decided that it's the red block that is the latest one. And so they will build upon that block effectively. And so the kind of the path of truth in our system is from the blue to the yellow to the red to the beige block now. And the green block is called an orphaned block. Effectively, it is dropped. Now, we don't really lose any data here, because the transactions that were in the green block, they may also have ended up in the red block, but they may have been differences. But people will not throw away the transactions until they see them in a block. So even if the transactions that were in the green block aren't in the red block, they will get picked up probably in the beige block or maybe in a later one and included in that. So the fact that we drop this block, this green block, is not a problem. We don't lose any data. The only thing is that it is a problem for the green miner, because they now have lost their transaction. So that transaction that went in to assign the block reward, that transaction is now in the red block. It assigns the block reward to the red miner. The green miner gets nothing for this. So the green miner has lost out. The red miner has won. It's unfortunate, but that's just the way it is. We're now following this path. That's the way the protocol works, and that's the way we will go on. And it's a nice way to make sure that our system will continue without any central authority. There will always be a way that we can choose what is our latest block, and we can send them a block. Okay, and it will continue, keep going like that. Okay, so that's how we build up consensus. Sorry, hopefully, can everybody see this slide? So I've only just seen someone saying you can, maybe you can't see it. Can you see? Okay, good. Are there any questions about that? Because that really is the essence of how proof of work as a consensus mechanism comes to its consensus. And it is really the heart of how Bitcoin, or how Bitcoin works. Great. Yeah, so you can ask me questions later if you have them. So, yeah, that's the consensus mechanism called proof of work. It is required because it's the incentive here, and the security is done by the incentivization and economic incentivization. It's important that this work that is being done is useless, because this puzzle we're solving, the results of that, the answer we find is effectively pointless. The results are not exactly thrown away, but we don't really gain anything from having done that. And people have tried to think of, surely it would be better to do something useful instead of just making these so many guesses and just throwing away all of this work. There are two reasons we don't do that. One, there's a practical reason that it would be difficult to do something useful and get everybody to agree on what this thing was. But also it would affect the incentive. If there was an incentive, if you've got an incentive to do the work that was not involved in just solving this puzzle, then it would make it would decrease the security of the system as a whole. So really the system does depend upon this idea of doing useless work and proving that you've done this useless work in providing a block. So to answer Vivian's question, yes, the block contains a transaction of the block reward, which pays the miner, and then all of the other transactions that the miner has decided to include in that block. So it will probably be most of the transactions that they have seen. Yeah. Okay, so that's the proof of work consensus mechanism. Drawbacks to it, the amount of energy that is involved. So the Bitcoin network, I've not checked recently. I think at one point, certainly a few months ago, it was using as much energy as Israel to produce just in solving this puzzle. So just to keep the network secure, uses a vast amount of energy. And a lot of these puzzles, a lot of the mining happens in large factories where energy is cheap. So in places next to hydroelectric dams, there's a lot of them in China, a lot of them in places like Scandinavia, Iceland, places like that where there's cheap energy, where it's cold, so they don't need cooling and things like that. You have these massive factories just full of specialized hardware trying to solve this puzzle. And it requires a lot of energy. So because of this, people don't like it, and so they've tried to come up with alternatives. There are alternative mechanisms. They're usually called proof of something. We have proof of stake, proof of space-time, proof of burn. You know, you think about an hour and there'll be a proof of it. They are more complex. Proof of work is quite simple to understand, quite simple to reason about, quite simple to understand mathematically. And it works from a security point of view. Incentives do align, even though environmentally it's problematic. Okay, so that's kind of the theory behind blockchains in general. I'll go on now to looking at programmable blockchains. How much time have we got? Okay, we've got a little bit of time, so it should be okay. So I'm just going to cover this in general. We're really going to cover smart contracts in much more detail tomorrow. So Bitcoin came about in 2009, and for a few years, people introduced other blockchains. They introduced different versions, really, of Bitcoin, trying different consensus mechanisms or tweaking the parameters, producing different cryptocurrencies, maybe for vanity or for laughs. But they were doing very much the same thing. They tried to increase what Bitcoin could do to make it do more than just be a store of value. But it's quite limited in what it can achieve. And so the next big step happened in 2014 when the Ethereum protocol came about. And it was invented by a guy called Vitalik Buterin, who had been involved in the Bitcoin scene for a number of years, and decided he wanted to make this, to realize this idea of smart contracts and to allow applications to exist on the blockchain, so that the transactions that happen on the blockchain are not just transferring value between two people, but they can be some small application, they can be some small computation that's happening on the blockchain. In Ethereum, I'm going to talk entirely about Ethereum now. There are other blockchains, but Ethereum is really the main one, and other ones developed later, but followed often a very similar design. But they use virtual machines, so I hope you're familiar with the idea of a virtual machine. It is really a simulation of a computer that lives within your computer. So within, say, your laptop, you could have a simulation of another machine running, another computer running some programs. And this is called a virtual machine. So the program is not running on your laptop itself, it's running within this simulation of a computer. And the Ethereum nodes all exist on hardware. For example, if you imagine they're all on laptops, the Ethereum nodes themselves would run on, say, a laptop, and the software on the laptop, the node software, would be responsible for the same things essentially that the Bitcoin node software does. So that is getting transactions, passing those transactions on to other people, receiving blocks, keeping a copy of blocks. But in addition, they do this extra thing in that they run a virtual machine, and this virtual machine runs programs. And these small programs are called smart contracts. And these smart contracts are what is contained in the state of the blockchain. So rather than keeping track of how many Bitcoins have been spent by different people, we're keeping track of the state of applications that are running in virtual machines. So as I say, the smart contracts are pieces of code running in the Ethereum virtual machine. This virtual machine, this environment, is highly restricted for various reasons, security and determinism, for example. The contract itself will be a piece of code that this application does, some state of the application, so whatever this application represents in the real world perhaps. And also this contract may have some ether associated with it. Now the ether is the cryptocurrency of Ethereum. So this smart contract can effectively control some value as well. And this allows some amazing ideas around autonomy and things that I don't have time to go into today. But the idea that smart contracts have control over value and effectively can have some autonomy and spend value themselves. Even though they're called contracts, they may not represent a contract in the legal sense between parties. If you want to do that, you obviously would have to add in extra things. You would have to write your application in a certain way and have it agreed that that's what the application means. But they do have a certain amount of automaticity, so they can be used to automatically transfer payments, for example, between parties. And they're typically written high-level languages. So we will see tomorrow, we will look at a particular language called Solidity, which is a language we can use to write our contracts. But on the blockchain itself, they're compiled down from that high-level language into a more compact representation called bytecode. But the high-level language is human-readable, much more friendly. The way they work, if Alice wants to create one of these smart contracts, she does that locally. She writes her little application and submits that as a transaction to the blockchain, to the Ethereum blockchain. This is gossiped around the nodes on the blockchain until everyone has a copy of her contract. And then if somebody wants to interact with that, each node will have a copy of that contract, and they can call a function within that contract. So they can interact with Alice's smart contract once it's been passed around and has become part of the Ethereum blockchain. And it's available on all of the nodes. And it's important to realize that the code, when somebody runs a function in Alice's smart contract, what they do is that they call a function, they pass in whatever parameters they have. So say they want to calculate a value. They want to add two numbers together. They want to add 2 and 2 together. So they pass in, they call a function in license contract, which is going to do this calculation for them. They pass in 2 and 2. What happens is that that calculation, this function, runs on every node on the Ethereum blockchain at roughly the same time. So each node, they're independent, they are autonomous, they want to do things and verify that everything is done correctly. So each of them has to do every computation that is done on Ethereum. It is not the case that the computation is distributed amongst people and they do a certain share of it. It's duplicated amongst all people on the blockchain. So they all do exactly the same thing. So you could have just one computer doing this and doing all the computations, but we want our blockchain, we want our computation to be verified, and we want consensus about it. And so we do it tens of thousands of times. Everybody on the blockchain does the same computation at the same time. So you lose efficiency, but you gain verifiability. Okay. As I say, there are some restrictions on what our smart contract can do. The first one is a concept called gas, and this is a restriction on the amount of computation that can be done. I'll explain this more tomorrow, but really this is to stop programs going, our little applications, our programs, going into an infinite loop. We wouldn't want our whole system to grind to a halt because our function was taking forever to come up with an answer. So we restrict the amount of computation that can be done. The second restriction, determinism. This is because we want consensus. We want everybody to get the same results when they do a computation. So we don't allow things like random numbers in our system. We don't allow you to get a random number generator and use that, which makes some things quite difficult. But it means that everybody who does the computation, who runs a function in the smart contract, will always come up with the same answer, no matter whether it's done on their laptop or on a Raspberry Pi or on their phone, whatever hardware they have, wherever they are doing this computation, they will all come up with the same result. And then oracles are used to get around a problem that, because we want this determinism to be true, we restrict and we say that you cannot, from within your contract, get data from the internet or get any data from outside the virtual machine. The only data that you can have is the data that gets passed in a transaction. And so we have this idea of oracles, which are third-party systems. They are not a blockchain. They have to be trusted, but they are. You choose to trust these if you want to get data from a data provider. You talk to one of these oracles. So, for example, you may get one of these oracles to send you the weather, and this means that even if your smart contract couldn't go itself to get the weather because it was behind a firewall, this oracle can go to a data source, get some data, say weather data, and then pass it on into smart contracts or into different blockchains as a transaction. And because all of the nodes in the blockchain receive the same transaction, we will get consensus. They will all receive the same information from each other. Okay, just a little bit about decentralized applications, which we'll come on to particularly next week. These are really the front end to the smart contract, some application logic, and this often happens. This often is done at the edge. So perhaps this application will be running on your phone, and then your phone will be talking directly to the Ethereum blockchain and connecting to a smart contract. But again, they can be centralized, but really decentralized ones will typically be at the edge. So you would download one of these applications onto your phone, and you will be running that application software, and that would then be going to the blockchain to interact with a contract. I mentioned IPFS there. That is a decentralized storage system. We'll come on to that in the last session. And these tend to be small, so they tend to be between say business to client or to customer rather than business to business. And often they will be involving a wallet. So if you download a wallet for Ethereum, that will may be like the decentralized application that you then use with the Ethereum blockchain. Oops. Lastly, just an example of some decentralized applications. There was one that came out at the end of 2017 called CryptoKitties, which swamped the Ethereum blockchain and kind of almost ground to a halt because of the popularity. This is kind of a digital Tamagotchi, I guess. It's a collectible that you have on the Ethereum blockchain. You collect these kitties, which they all vary in some aspect. Their ears may be different colors, or their eyes may be different, whatever it is. And people pay, up to hundreds of thousands of dollars for particular ones of these, and collect and trade these things. But there are many different types of applications, and we can cover that if you want to talk about that. Yeah. So in summary, I think blockchains should definitely be seen in the context of decentralization. And really, if you understand decentralization and keep that uppermost, that will really help you understand how blockchains work. The way that we overcome some of the problems that have existed in getting from centralized to decentralized systems have often involved cryptography. So that is why they really developed out of developments that happened in the 70s. But the early attempts at cash didn't work very well. They didn't really get the incentives right or understand how to stop double spending. And Bitcoin really did solve these problems. And then we came to see application blockchains when we got Ethereum in 2014. And there have been a number of different types of those kind of blockchains ever since. And are currently very popular, as we shall see when we do some programming on Ethereum tomorrow. Okay, I think that's everything. I'm really happy to answer any questions. It's been quite a lot of information there for people to take in, so I hope it was useful for you.
Thanks for that great talk, Laurence. It was really, really clear, really, yeah, it never gets old. I love it. But yeah, please fire away if you have any questions. And after that, I'll announce the raffle winner as well.
So someone saying about programs to install for tomorrow. No, you don't need any programs. We will use a development environment that is within your browser. So yeah, as long as you have a browser, you'll be
fine. Yeah, that was a good question. I was very worried about that, but it's all run in the browser. Any more questions? Okay. But yeah, just to once again also say thanks to Laurence for giving a great talk. We'll see you again tomorrow. And also thanks to Oxford Women in Engineering, Science and Technology, OxWEST. So we organized this talk with them jointly, looking to get more and more women into blockchain spaces and coding spaces. And essentially, for all, you'll be surprised how far just the basics will take you. It could spur a really good interest. And, before you know it, you could be pitching for funding at a hackathon that we've got actually coming up with ENCODE Club in the near future. So after that, I guess, thank you again, Laurence. We'll upload a recording of the lecture and the slides so we can send them around. And finally, the raffle winner. So out of the remaining participants, I had a little random number generator. And the winner of some ether, the amount is yet to be decided, but it's normally around the 0.1 ether amount, is Morgan Braybout. So could you please come down and claim your prize of 0.1 ether? Yeah. Okay. Awesome. So more. So yeah. Okay. Cool. So you verify that you know it. You've got it. Quite simple. Send me an email with your Ethereum wallet address, and I will send you 0.1 in Ether. Well, maybe not exactly, but need to check because we're actually doing quite a few raffles at the moment. If you need help setting up your Ethereum wallet, if you don't have one already, I recently did a video with our previous raffle winner, Laletta, and it's on our YouTube channel. If you want to see how to set up a wallet. And if you have any questions, just pop me an email. You can find it on our website. But other than that, I think that's it from me. So congratulations, Morgan. And yeah, actually, there's any more questions or comments? It's great to see so many people here. Okay. No. All right. So that's it. Anything else you wanted to mention, Laurence? Or
No, just thank everybody for your kind comments, and yeah, I'll see you tomorrow. And yes, sorry, I forgot to have a break. Yes, we'll definitely have a break tomorrow. Apologies for that.
cool. Okay, great. So have a great rest of the evening, and thanks again, Laurence. Awesome. See you tomorrow.
Thanks. See you then.